morning, afternoon. Let's see, I was going to talk about what's going on in X.org right now. Is there a volume to turn down slightly? Is this the volume? Like that? That's not still, is that still audible? Yeah, okay. There's quite a bit of feedback before. So usually I talk about X.org in kind of an abstract fashion and talk about what we are doing. This year I really wanted to start focusing on who we are and encourage other people to get their pictures up on the screen in the coming years. This is a picture of Adam Jackson, who has been working very hard on X.org release management for the last year or so. He just finished X.org 7.2, which came out last week. It contains Xserver version 1.2. It contains Xlib based on XCV. A whole bunch of other cool stuff. Actually, this is one of the first releases that's really started taking advantage of the modular process and pushing the envelope of our modular release system. Usually, an X.org release is. You have a question up there? Oh, just hand waving. I don't think with a camera, so you can't be on TV if you're raising your hands. Adam actually released the Xserver itself, version 1.2, sometime way back in early January. But the full Xserver release wasn't ready for release at that point, largely for documentation reasons. And so it's kind of interesting, we started seeing people take up release 1.2 of the Xserver and not wait for the full roll-up release of Xorg 7.2. Coming close on the heels of this release, I'm going to do an Xserver 1.3 release the next month, I hope, and start trying to push the pace of releases up in individual projects so that we can get features out into distribution in a more timely fashion instead of a 6-month schedule. What are some of the features in Xorg 7.2? We did a lot more auto-configuration stuff. So the system will auto-detect monitors, will auto-detect input devices. You could run a reasonable Xserver now with no Xorg.conf file most of the time. That's sensible things. It doesn't always do what you want, but it usually does sensible things, which is good. We're moving more in this direction to get rid of the configuration file. One of the keys to getting rid of the configuration file, of course, is to be able to change things after the server is started. So you can fix the configuration without having to restart the server. Yeah, the first of many pictures. The one thing I noticed in collecting pictures for this talk is that most of the Xorg developers apparently spend a lot of their time drinking. I know that's hard to believe. This is Dave Earley at a conference. He has actually 2 beers and 2 hard ciders, and he's going at them quad-fisted at this point, apparently. Which is appropriate because Dave Earley actually works on a lot of different pieces of X.org. He's been working on the Radeon driver, doing R300 and R500 support. He's in a very unique position because he actually has documentation for all the ATI hardware as a part of his other job, which is to work in the gambling industry, doing hardware and software for gambling devices. So he has to be very careful because it would be terrible for any of the documentation that he has for the ATI chipsets to leak out in the form of source code. So he has to be very careful in his development efforts on the Radeon stuff. What else do we have here? Other people that have been working on the Radeon developers has been Karen Schmidt here. Where's my cursor? There it is. This was from, I think this was from LCA, the Linux Conf Australia, at dinner time. It's a nice meeting. So what's been happening in the Radeon driver? The Radeon driver we've had, the Radeon driver is not supported at all by AMD at this point. So this is a pure reverse engineering effort by these developers. They're going in and actually taking the existing closed source Radeon driver and making applications and driving the driver with the applications and seeing what happens out the other side to try to deduce how the hardware works. It's a tedious process. A little docs go a long ways, and they have none. At this point, the R300 driver, the reverse engineered R300 driver, is fairly usable. The R500 driver is just barely getting started. They hope to have some 2D and mode setting code relatively soon. I think Michelle Danger has a pretty good demo of the R300 driver now running on this laptop. So if you catch him in the hallway, you can get him to show you what the R300 open source R300 driver is up to. Dave's been working on Random 1.2 support with the resize and rotate stuff that I can show you in a while. And Michael's been working on some of the more 3D stuff. This is Michelle Danzig, who's here somewhere. Is he actually here in the room today? There he is. So I took this picture earlier today. This one does not have him with a beard yet. It was about 10 o'clock this morning. You don't start drinking at 10? 11. He's apparently a new X.org developer. Okay, moving on. Another important driver that we have now is we're trying to reverse engineer the NVIDIA hardware to build an open source NVIDIA driver. The project that's doing this work is called Nouveau. This is Jeremy Cole, one of the developers. I asked all the Nouveau driver developers to send me pictures. None of them did. Fortunately, I found a picture of Jeremy, who was apparently, I think, in an advanced state of inebriation. Otherwise, he wouldn't have a fork in his mouth. There's something about 3D graphics and heavy drinking. It's a good combination. The Nouveau project right now, they're actually starting to make some progress. It's not a driver usable by normal users at this point. But I think what we learned from the Radeon R300 reverse engineering project was that the driver is unusable and barely functioning for an amazingly long period of time. And then all of a sudden there's a big knee in the development curve, and it goes from being unusable to very usable in a short amount of time. And I think the Nouveau project is getting fairly close to that. So I expect to see in the next 6 months or so people being able to use the Nouveau driver on their, at least for 2D graphics, if not for 3D as well. They're getting solid polygons painted on the screen right now, and that's a big step to actually getting triangles up on the hardware. Apparently they need to use the new texture memory management system that Tungsten Graphics has been doing for the Intel chips. It's been moving into the Radeon driver. They're going to need to migrate that into the Nouveau driver in order to get textures at all. It's kind of an amazing amount of work. So these guys are brave souls. They haven't gotten any death threats like the Radeon driver developers apparently do. But I don't think NVIDIA is very happy about their particular efforts either. In a slightly happier frame of mind, this is Eric Anholt, one of my coworkers at Intel, who's working on the Intel driver right now. He's drinking. I think those 4 empty glasses in front of him are probably his. Yeah. So the Intel driver is making really good progress these days. We actually have the combined efforts of 2 companies working on it right now. Tungsten Graphics was under contract with Intel for a long time to support the Intel driver and do a lot of the work in it. And they continue to do a lot of work in the Intel driver in the 3D space. And then Intel itself, we have a team of about a dozen people at Intel working on the driver, on the open source driver right now. Eric's one of the key developers there. What? You've never met Eric? Oh. So conferences are a time when developers who are working on the same code base get together and meet each other, which is kind of cool. And apparently I was supposed to bring Eric to this conference. I apologize. I had actual work for him to do. So what's going on in the Intel driver right now? The big change over the last year is that Intel has built a team internally for driver support and driver development. And that involves QA, it involves development, and it involves distribution, and it involves support with OS vendors. So we're actually interested in getting Intel driver support into existing operating system distributions. Have half a dozen QA engineers making sure it works on legacy hardware. So if you have an i830 laptop, you can run new drivers. So that's a big part of our effort. It's been an important thing for us to do. The Intel drivers where I'm doing all my Random 1.2 development work. The Random 1.2 development work is not limited to the Intel driver, but that's where it's starting, because I have to start with something, and that's what I'm paid to work on, so that's how it goes. One of the interesting and exciting changes that happened in the last year that was started in the Intel driver is the new texture memory management system. with any UMA hardware, so any of the AMD or NV or Intel hardware that uses system memory for graphics. You used to think of that as kind of a bad thing because it was a performance problem, but it turns out it has some pretty phenomenal advantages in terms of uniform graphics performance. One of the things we're able to do now is we're able to take the GTT table, it's basically an MMU for the graphics chip, and map all the physical memory dynamically into the video card. So I can actually, with the new DRI infrastructure for memory management, I can draw to any page of memory. So I no longer do I have fixed allocations of texture memory and fixed allocations of 2D pix maps. When we finish this work in the next year or so, we'll be able to draw all of physical memory and virtual memory as well in the future beyond that. So that's kind of exciting. We're finally moving out of the limitations of video card memory spaces and into a space where we have pretty much unlimited memory, which is kind of cool when you start thinking about composited desktops with thousands of windows, each taking millions of pixels. I wish I had stock in a memory company. Not so great for a CPU company. Here's another developer on the Intel chipset, Keith Whitwell, who did all of the 3D development on the 915 and 965 chipsets, another tungsten developer. And I wanted to have a picture of Alan Horhane, who's been, this poor gentleman. So the Intel contracts that he was working on specified that he was to use the BIOS for mode setting. And then they said, oh, but we want some additional mode setting support. So we want to be able to do things like rotate the screen. We want to be able to do things like have different modes on internal, external displays. BIOS doesn't support any of that. So he had this amazing Rube Goldberg mode setting adventure where you kind of used the BIOS a little bit for some primitive mode setting, and then he just stacked this code on top of it. So the man with the limitations and the amazing implementation. Unfortunately, we've thrown all his code away. I hope he's not there. I'm really impressed with what he did. And certainly the architecture inside the driver that he put together has been a solid foundation for us to work on. Okay. A big change in the last couple of years in X. We had this, originally X drivers were all based on direct access to the hardware, and when you wanted to program a video mode, you would go in and tweak the VGA registers directly. You'd go in and reprogram the hiding directly on the VGA port. Because all of the cards were basically VGA cards, this worked really well. They were all very similar. You had ET4000 or whatever, ET1000, whatever your video chip was. It all looked like a VGA chip, and you could reprogram the video mode with a relatively small piece of software. Then along came Windows 95 or Windows 98, sometime in that era. All the video cards all of a sudden grew their own mode setting hardware. So in order to program a new video mode, you had to know a lot more about the video chip than you really wanted to. And it became common for X drivers, or at least a few X drivers, to start leaning on the video BIOS itself for mode setting. At that point, the video BIOS grew some extensions, and it knew how to do linear frame buffer mode settings, so you could actually get the video BIOS to come up in a mode that the X server could actually use at that point. It was kind of neat because you had to write very little code in an X server to get something running. You asked the video BIOS to program a mode, and bang, you were running in a frame buffer, and then you just write a little acceleration code and you have an X server. I think one time I needed to do some performance analysis on a new video chip, and I had an X server running accelerated on this hardware in about 3 hours, using the video BIOS to go on the mode setting. Well, that was great for about a year. Oops. It was interesting for about a year until we discovered that the video BIOS didn't do everything that we wanted. And the one problem with the video BIOS is if it doesn't do what you want, you can't do it. So for instance, what I'm doing right here, I have images up on the screen here, and on my laptop I have my notes. So this is one machine driving 2 screens. The video BIOS is no emotion. You can't use the video BIOS. What Alan Horhane had to do for the Intel driver was actually use the video BIOS to program the mode, and then go fix it up by touching the registers directly. So that gives you the best of both worlds, where all of your video BIOS bugs are exposed, and also all of your mode setting all of your mode setting code has to know a lot about the hardware. So you got all the bugs in the BIOS and all the bugs in your own code mixed together and causing all kinds of problems. So this is Thomas Winneshofer, who's an attorney in Austria. He said for the sys driver that was a bad idea, and he was right. He was way ahead of the rest of us. He actually came up and said, well, for the sys driver, we're not going to use the BIOS anymore. We're going to switch to native mode setting. Because there's a lot of things I want to do that the BIOS can't do. And so he converted the sys driver 3 or 4 years ago to using native mode setting. He struggled with that for a long time. There are a lot of things it still can't do. But it was a good transition. Another person working in this space, oh, this picture is not visible at all, I apologize. This is Luke Verhagen. I don't know if he's here today. He's probably actually listening to Egbert's talk right now. He's doing the same thing to the VIA driver, except there's 2 VIA driver projects right now. The old VIA driver, which is based on the BIOS-based mode setting, and this new Unicorn driver, which is native mode setting. And they're trying to figure out how to get the capabilities in the BIOS-based driver, how to not lose those capabilities and yet still have native mode setting. There's a lot of stuff that Luke's driver doesn't do yet. What? So we're working through some political issues there. So we actually have 2 VIA drivers currently for Xorg. And the Intel driver right now, I have recently transitioned it over the last year from BIOS-based mode setting to entirely native mode setting, as a bunch of the requirements that we have for the Intel driver and what I wanted to do with Reindeer 1.2 just couldn't be done with the BIOS anymore. Yeah. What? This is Daniel Stone. He's okay. This is a pretty accurate picture. I had a lot of picture choices for Daniel. This is the one when he looks the least drunk. Daniel Stone is an Australian who's actually currently working up in Finland. So he's moved from 40 degrees C to minus 40 degrees C. Yeah, he really needs to be drunk. He must have been drunk. He works for Nokia right now, and if any of you have seen the little N800 handheld computers that, what are they called? Personal internet tablets. Yeah, okay. It's a little
bedside porn viewer.
Yeah. They have a prop-up stand now, so they don't have to hold it. They gives you 2 hands. Apparently they know their market. Hope this is not making fun of me. So Daniel is kind of he's a really fun guy. The cool thing is, one of the requirements they wanted for this new 8800 tablet is to be able to use Bluetooth input devices, Bluetooth keyboards, Bluetooth mice, and that kind of stuff. And he said, oh, I'm going to be able to use multiple keyboards. Well, in order to do that, I have to go off and fix this entire X input infrastructure so that it can handle hot plugging of input devices. And so he took this tiny little feature that his product management came down with, we need to support Bluetooth keyboards. And he said, I have to do all this work in the open source Xorg project. So this is a classic corporate engineering story, where you take a tiny feature that's required by your product and blow it out into this enormous open source project. So he's actually spent the last year digging into the bowels of some of the nastiest parts of the X server, the X input extension, the X keyboard, the XKV extension, and all of the input event processing inside the X service. And what he's done is he's ripped all that code out and replaced almost all of it at this point, I think, to the point where you can actually start up an X server with no mouse or keyboard connected to it. And you can actually hot plug all the devices after the server started and will dynamically determine what kind of keyboard, what kind of mice are connected, and give you the ability to add additional keyboards, so you actually have 2 keyboards and be going at them simultaneously. I think that goes from 2 hands-free to 0 hands-free. I'm not sure that's addressing his market or not. Which is cool, because now you can actually plug in additional keyboards into your laptop, and you can change from, like my laptop has a Japanese keyboard layout, I can change it, I can use a French layout keyboard. In addition, I can switch back and forth between 2 different keyboards, which is very useful, and use them at the same time. He actually has a friend of his, I think I have a picture of him as well. Yeah, there he is. Peter Hunter. I'm sorry that the picture's not very in focus. This is an Austrian who's moved to Australia. So it's kind of funny because Peter lives in Adelaide and Daniel comes from Melbourne, and now Daniel lives in Finland and Peter lives in Australia. So we got long distance commuters. Peter is working in at a research lab in University of South Australia. No, I think it's University of Adelaide. I don't know. There's 3 universities in Adelaide. It's a town of 100,000 people. I'm impressed they have that many. But he's actually working in multiple X pointers. So he's not interested in being able to use multiple mice on the screen at different times. He's interested in using multiple mice on the screen at the same time. And I wish I had a movie of him doing this. I've actually watched him operate 3 mice simultaneously. Which is really funny. He's got 2 hands, and he really is doing the other one with his chin. It's cool, yeah. Apparently, he can operate multiple mice with 1 hand, although he can't click buttons as effectively. But he's written a new window manager that allows you to grab the 2 corners of the window separately and like move it around, drag it. Yeah. Oh yeah. So the question is, so what if you have a multi-touch screen, and you put all 10 fingers on the screen simultaneously? What do you get? Well, because Daniel has this hot plug input architecture, and because Peter's stuff supports multiple cursors, it could work. I don't know. Well, one of the interesting things about Peter's work, and I think one of the most aggressive things about his work, is that he's trying to make multiple cursors work using the core protocol. So he's trying to make it so that you can actually send mouse press events to 2 different windows and not have and let 2 different windows think they both have the mouse. So you can be operating 2 menus simultaneously. And he's trying to figure out semantics so that our existing architecture, which all believes there's only 1 mouse, will work with multiple mice. And I think he's got a really hard job ahead of him. Pieces of it work okay. Most of it doesn't work so well. Most window managers, for instance, get really confused when you click in 2 windows and try to drag them simultaneously. He found one Fluxbox apparently works. It's amazing. I don't know. It's pretty cool. So he's fun. I got to meet him in Australia at LCA, and we brought him over for the X Developers Conference. And another heavy drinking Austrian. I know it's a shock. Let's see. Here's another Portland native. One of the things in Xorg 7.2 is a change that most of you will never notice, but it's very fundamental to the system. We've lived for nearly 20 years now with XLive, the C binding for X protocol being this library called XLive. XLive was written in an era when we only had 1 CPU, pretty much for the entire lab. So this notion of thread handling and multiple applications and that kind of thing, not so big. And the other problem with the era of XLive is it was written before the era of shared libraries. I know it's hard for you guys to imagine. In 1987, there were no shared libraries on any Unix systems. And so every application got to link statically against every library. The result of that was kind of odd. It meant that in order to keep program linking from breaking, that pretty much every new feature that went into XLive. So XLive drew things like internationalization support and XKB support and color management systems. So XLive had a couple of pretty bad bugs. You couldn't do multiple threads, and it was fusion mode. So a team at Portland State University, led by Professor Massey, has been writing a new X protocol binding called XCB. XLive is a megabyte. XCB is 30 kilobytes. So it's a factor of 30 smaller or something, which is pretty cool. The big change for Xorg 7.2 is that XLive now uses XCB. So when you run an X program that talks XLive, your X application is actually using XCB for the underlying transport. Does this change how the program works? Not at all. What it does do is it enables application developers to start migrating their applications to XCV native interfaces. And eventually we can shed this excellent load. We can get rid of this megabyte of memory. We can make our applications thread safe and world domination. And here's another of his students. It's not working very well today. This is Jamie Sharp, who's done most of the XCV implementation. XCV actually uses an XML description of the protocol. So you have a textual format that describes how the protocol works. That means that you can generate C bindings, which XCV does, for a library. You can also generate documentation for the protocol, because you can put documentation in the XML descriptions. You can also generate a list binding for the protocol from the same XML, or Python binding, or whatever you want. The other neat thing we're going to be able to do is we're going to be able to generate the server-side protocol interpretation code as well. Byte swapping code, all this cool stuff we can do with the description of the protocol. Until now, all of this stuff has been done by hand. Every XLib marshalling and every server unmarshalling function was written by hand. Over the last year, Coverity and other people have discovered half a dozen or so bugs in the X server, which are buffer overrun bugs and other simple bugs like that are caused by bugs in our protocol unmarshalling code, which was all written by hand. So if we had started with this descriptive format of the protocol being automatically generated in C code, we could have saved ourselves 6 potential local root compromises to your system in the last year. And I don't expect to have that number go down in the next year or so. I expect to keep having issues like that until we can convert to the XML descriptions and use that for the generation. Here's another XCV developer, Ian Osgood, who's been working on a bunch of the extensions in XCV that's been converted over as well. At this point, I think XCV covers pretty much all of the X extensions. So it really is a complete replacement for XLib at this point. And it's ready for use. And your systems will have it pretty soon. Let's see what else we have. Other work over the last few years. This is Matthew Allen, who's probably here. He may be in the X conference right now. He's been working on a couple of things. Matthew's been working on Zephyr. Zephyr is kind of a cool little project. We used to have an X server called XNest. We could run an X server locally, and the XNest server would actually forward all of the X requests over the wire to another X server, and you'd have a window on another X server that contained an X session. That was kind of cool. One of the problems with XNest is that it actually created remote objects for all of the things that you were doing. So when you created a window in your X server, from the local XNest server, it would shadow that and create another window in the remote X server. All the image formats and fonts that were available were the ones that were available from the remote system. So there was a lot of limitations with that, and there wasn't any particular reason for that. What Zephyr is, it's a dumb frame buffer based X server, and so it paints the screen image into a local frame buffer, and then copies those images over the wire to a remote X server. So you have a couple of advantages. You get all of the whizzy new extensions that you could ever want locally, because it's just rendering it up frame buffer code that you have that supports everything. And the other cool thing is you can disconnect from it, leave it running, and connect up a new X server to it, and paint multiple X servers. That's some things that he's hoping to work on in the next year. One of the things that it did gain this year is the ability to dither down from, so if you have a 24-bit Zephyr screen, you can actually send that out the wire to a 16-bit remote X server and dither the result down and get some resolution reduction that way, which is kind of useful. Matthew actually works in a company called OpenHand, which has been working on the N800 device and a lot of other embedded devices, which is pretty cool. So we have a little consulting company that does embedded X work. Let's see what other notes about what. Oh, and Matthew's also been working on fixing up the X resource extension and X res talk. He does a lot of embedded work. What's his biggest problem in embedded work? He always runs out of memory. So he's very interested in analyzing and tracking resource usage of applications in the X system So he's been maintaining the X resource extension, which lets you see what clients are using, how many resources, and also monitoring the external monitoring applications so that you can monitor resource usage in real time. Another thing that Eric's been working on is EXA, which is a new acceleration architecture. This time he's drinking Pepsi. What? Oh no, it wasn't. That was at, the last picture of Eric was from Guadalajara, which was down in Villanova, Spain last summer. We had a lot of sangria. A lot of sangria. Related to the diet. You know you can get a giant pitcher of sangria for like €2? Great. So he's been working on a new acceleration architecture called EXA. The whole goal of this is to make it easier to write really fast X servers. And in the last couple of months, with the notion of the new memory allocation system that we're doing and some other new algorithms for doing accelerated rendering, it's pretty clear that we can do all of the acceleration that we need to do, all of the drawing that we need to do with the graphics engine. It used to be we had a whole bunch of rendering that we needed to do, we thought we could only do in software. So we had these glorious, grand migration schemes of when you needed to do stuff in software. You pull the image out of the video card, carefully render in software, and put it back in. Expands and migrate back and forth. Eric came up with a much simpler scheme. Everything can be rendered with the accelerator now. So what you want to do is you want to get everything onto the video card. And the only reason you don't put everything into the video card is because your video card doesn't have enough memory. So now he has a simple scheme for getting everything into the video card and then noticing where things have been rendered in the video card, so that when you need to page that image out and put another image in there because you run out of memory, you can actually track which areas of the image in the video card have been changed and pull just those little subsets of the image back out instead of having to pull the whole image out. So you can imagine painting a giant 1,000 by 1,000 window on the screen, and you update the cursor down at the bottom left-hand corner. So you push the entire million pixels onto the screen, paint the cursor with the hardware, and then you say, oh, I need to draw this other window now. So you have to take this whole million pixels back out of the frame buffer and put a different million pixels into the frame buffer. Well, if you kept a copy of those million pixels before you painted the cursor off screen, all you need to do is copy the cursor, the part that was modified, on the screen, back off screen. And so that's what this new EXA damage track stuff does. So I'm hoping that EXA can become a viable acceleration architecture in the next year or so, probably sooner than that, and we can take advantage of the video memory that you have and the acceleration that we can get with the simpler architecture. It's going to be good. That was kind of what it was. I wanted to talk a little about the OLPC. I know Jim gave a presentation this morning about OLPC. As an artifact, it's not any more important to me than any other PC architecture. But in terms of a development process and what their platform targets are, I think it's very important. They have some very critical resource limitations in the environment, and they're starting to, and because of the large number of units they're going to be deploying that are running the software, all of a sudden their interests become very important to us because they're going to ship a large number of units, and all of their units are very resource constrained. So Jim's starting to get starting to push a lot of people into reducing the amount of memory the applications are using and making sure that they are as scalable rendering architectures so that we can cut down the amount of CPU resources they need so that applications can be used in a smaller, lower performance platform. I think it's really important. And Jim, of course, works with J5, who's another OLPC developer, working in application development and trying to build a UI that can work in this resource-constrained environment and still provide a rich experience for their target audience, which is pretty cool. This is Dave Revman here. I don't know, can you see him at all? No, not so much. Dave Revman, he showed up, what was it, about 2002 or something, and put together a bunch of accelerated rendering code for Cairo. And he took that and actually built an Xorg out of it called XGL. Over the last couple of years, he's become a very responsible citizen. It's kind of frightening. He started out as a wild kid. He's built Compiz, the compositing manager. How many of you, I've seen some of you have seen the Compiz demos or something, a 3D compositing manager. Unfortunately, I can't run them today. But yeah, the life of developing an Xorg mostly doesn't work. So he's actually put together a couple of things in the last year. He's been stabilizing Compiz. He has a nice plugin architecture now, so you can add new compositing modules. But over the last 4 or 5 months, he's starting to finish one of the last problems with composited desktop, and that's the one of transforming input as well as output. If you've seen ever seen the expose application in Mac OS 10, you know that one of the things you cannot do when you have the windows minimized and shrunk it down is you can't manipulate the windows in their transformed state. Which is kind of okay for expose. They don't, you can imagine that you can drag windows around and look at them, but you can't manipulate them in that small state. And for expose, that's fine. Expose is, trying to let you manipulate a large number of windows and navigate a larger space than you would otherwise be able to navigate on your desktop. But if you're talking about a screen magnifier, where you're talking about a tilted environment, where you're transforming images for projection, you really want to be able to manipulate the windows in that transformed space. And David is finally solving that last problem in our composited environment by doing some server-side input transformation. I know I've talked at several conferences about various input transformation schemes I've looked up. None of them have worked, but it looks like David's really actually going to succeed. And that's exciting to see the final piece of our composite transformed desktop fall into place relatively easily. No work on my part. That's always the best part, right? Other people just say, oh, here's the stuff we needed. We had Xorg board elections this last fall. We have a new board. Egbert is one of the ongoing continuing members of the board. He's actually presenting in another hall down the way today, so he's not here. I wanted to show you his picture. I don't actually have pictures from the rest of the board members, which is kind of sad, because they're all pretty neat people. So the board we've made a couple of changes, and we're hoping to make more changes. The Xorg board is encouraging people to, if you're a group of ex-developers and you want to do if you want to put together a meeting to do some concentrated development, we're interested in hearing from you, and we can help you find this place, and we can help you with travel funding and funding for renting a room and that kind of stuff. So if you have concentrated ex-development to do, come and ask us. We can help you put that together. We're running a couple of conferences this year. XDC, the Ex-Developers Conference that was in Palo Alto a couple weeks ago, and we're hoping to put together another Ex-Developer Summit later this fall, hoping to do that in Cambridge. That's not set yet, though. Matthew Herb is an OpenBSD developer who's at the conference this week. One of the things that I've noticed him doing over the last year is really taking a lot of responsibility for responding to security alerts that we get and making sure they get driven to completion and the bugs are filed and the bugs are responded to and the disclosures are happening on time. And I really want to thank you for that. OpenBSD certainly gets a lot of credit for its ongoing support of OpenSSH development. And in this particular case, Xorg is getting huge advantage from their focus on security and stability by having him help us with our security responses. We had a couple of conferences. Here's Carl and Daniel drinking heavily at, not Carl drinking, but at DDC last year in Ottawa. And here's Jamie and Carl and Bart at that DDC in Ottawa. That was a fun time. Okay, yeah, I know Hey Dice's first picture didn't have him drinking, but there he is. This is might have been at Warwick or something. And there he is again. So I have some time for questions or comments if you have any. We'll move on to the next talk. Wait for you to think of a question. the question is whether Intel will offer dedicated graphics cards. I'm sorry, we need to talk about the future of that product. Yeah. Other questions or comments today? Yeah. So the question is, what about moving drivers to kernel space? That's actually something that I'm hoping to be able to work on this next year. The video drivers, there's a lot of different pieces to a video driver. There are pieces that we already have in the kernel today. If you look at the way our 3D drivers work right now, we have a significant kernel component. The kernel component manages interrupts, it manages DMA transfers, and it manages some resource sharing between applications sharing a video card. That can't be done anywhere but in the kernel. You have to manage interrupts in the kernel. The other piece that I'm hoping to move into the kernel in the next year is mode setting. Not because I think mode setting belongs in the kernel, but because I want to be able to support suspend and resume, and I want to be able to support panic messages coming up on the console. So I'm working on an architecture to move mode setting into the kernel so that I can have a kernel driver that supports DMA, supports interrupts, and supports mode setting, so I can actually have a comprehensive single kernel driver for the video driver. What I will leave in user space is the generation of the contents for the ring buffer, the generation of textures, the generation of coordinates, just like we always have. So we're going to leave this kernel user split like we've had for the DOI and the X server for a long time, where the user mode driver is generating the content and the kernel mode driver is managing the content as it's delivered to the video card. So one of the things that most kernel drivers have that you see in a typical driver environment is the kernel driver provides a uniform interface to user space, where user space sees the same API for all video cards, like a disk controller. What does the disk controller do? Well, it provides block level access. And so every disk controller looks exactly the same in user space. For graphics cards, that doesn't seem appropriate. I'm not going to provide a uniform API to user space for the graphics card. We're going to leave the bulk of the data generation in user space, because the amount of data that the amount of transformation you need to convert a common API into a card-specific data is enormous. Doing that in kernel space makes no sense. In particular, one of the things you need to be able to do to drive a graphics card right now is you have to be able to compile programs for it. GLSL, the GL shading language, or even the older ARB texture program, the ARB Vertex program. Those are all programming languages in an abstract sense. The common API is not, it's not a common instruction. The common API are these programming languages, and you actually have to compile them. So the only way I can provide a uniform API for all graphics cards is by putting a compiler in the kernel, which makes no sense. I'm not planning on doing that. Similarly, when you're generating vertices for video card, the vertices need to be in a card-specific format, which is a tremendous amount of code because the amount of data that you're transferring is relatively large. And so in order to have a common API for all of that, I would essentially have to have all of GL as my API in order to take all the vertex formats that you want to be able to transform into the card-specific data format. So again, a very broad kernel API. By putting a kernel API that focuses on taking the instructions that the user library is generating and queuing them for DMA to the card, just doing the DMA transfers in kernel space, I get the security, I get the sharing, and I get the advantages of kernel space without bloating the kernel with an entire implementation of GL. So that's the plan. And that's how we've done it. And not only is it how we've done it, it's how a lot of other systems have done it as well. Because graphics cards are much different than any other peripheral machine. They're frequently much more powerful than the processor. And we're not getting slower yet. What? Oh, it's also very similar to this?
Yes.
Yeah. Yeah.
But I hope to provide framework for
Oh, yeah, the frame buffer is going to exist. I'm hoping to just build a frame buffer on top of this architecture. It's got mode setting, it's got memory allocation systems. Doing a frame buffer is pretty easy. Yeah. Other questions and comments? Yeah. The open graphics project, people building open source graphics hardware. I haven't seen their hardware yet. Certainly, I'm interested in having a driver for their hardware in Xorg and cooperate with them. But I don't really know. Is there more to your question? Right. Yeah. Yeah.
And what about EGL? Is it dead? Is it alive? Can you hear me from that?
The questions about EGL, the X server based upon GL, I've had some pushback from that from driver writers or GL drivers. One of the problems one of the problems that's been expressed to me and that I kind of agree with is that GL is a very fluid spec, and in GL, what looks good is correct. So if it looks good on the screen, it's considered correct by most people using a GL application. GL applications are used in animated environments mostly, and so the quality of pixelization that they're interested in is much more related to the performance that they're able to get the pixels up on the screen than which pixels they actually draw. Which is to say, GL implementations typically focus much more on performance than adherence to some abstract specification. And as a result, when you try to do a 2D X server on top of another GL library, you don't get any pixelization guarantees. And in fact, oftentimes the look of the same GL execution on two different GL libraries is dramatically different. And that's okay if you're playing video games. It's okay to an extent if you're doing CAD drawing. It's not okay when you're doing most 2D applications where you're looking at text being displayed on the screen or you're looking at icons being drawn on the screen. Most people are not interested in having them be several pixels out of whack. So the problem is in order to build an X server based upon GL, you need a solid base to build on. And GL libraries don't provide us a precise enough specification or a constrained enough implementation space for 2D applications to sit on. So when you build an X server on top of GL, what you end up doing is you end up artificially constraining what the GL libraries that you're going to use can do in terms of flexibility of rendering algorithms, the flexibility of polygon pixelization. So all of a sudden, these GL libraries feel very constrained into how they can explore the performance versus quality space in their implementations. So several GL authors have said, we wish you wouldn't do that, because it makes it very hard for us to write a GL library that satisfies the performance requirements of our other customers. So I don't know. Maybe at some point GL will become well enough specified that it makes sense. Right now we have some advantages that 2D graphics are very primitive. I need to be able to fill solid colors, fill gradients, and paint textures. The number of operations that I need are very small. It doesn't take very long to write a 2D driver for a typical card. So the amount of code saving that we're getting is not very large. And the amount of pain that we're putting on the GL implementers is fairly high. So right now, I don't think it makes a lot of sense. One of the architectures we are looking at is to retain the existing 2D API, but allow specific driver writers to leverage their 3D implementations for the execution of 2D operations. That's a project called Glucose, where a particular driver author, say you're writing the NVIDIA driver, writing an Intel driver, you know how your 3D library works. You know exactly what it does. The rasterization is satisfactory to you. So instead of writing another big pile of code specific to your hardware, you can just call into your 3D library. And because we can now call GL functions from inside the X server with AI-GLX, you can implement 2D operations using GL calls. But because we're making this a function of the driver writer instead of a global decision for all operations, That means the driver writer gets control over what pieces are implemented using his GL code and what pieces are implemented with custom driver code. So we're making instead of making a big switch to a GL-based X server, we can make a slow migration where we slowly use different GL things for areas where it makes sense. Especially when you talk about the render extension, where the pixelization requirements are much different than the Core X protocol. So I don't know. Right now, it looks like a combination of AI GLX makes more sense. I probably have, yeah.
Maybe one last question.
Yeah.
They also working on like LLVM, like these things,
LLVM?
the little virtual machine stuff that we
I haven't heard of LLVM at all. Sorry. A million projects out there. Cool.
Okay,
Thanks very much.
Then we have to